Alright, so we did the simulation for about the first 35 minutes of class. That's under my website. Alright, here we go. If you're working on something else, keep it away for now. If you did not quite get finished with the simulation, I'll try to give you guys some time on Tuesday during intervention to wrap it up. Who's 90-ish% done? Awesome. So if you're more than 90, of course, it's already in the box. If you're done, it's in the box. If you're not quite done, then you pull out. All right, so we're going to talk about the ideal gas law today. It probably will take us about 10 or 15 minutes to get a hold of it, and we're going to talk through a couple questions with it. So this is the kinetic molecular theory, or the relationship between ideal gas law and kinetic molecular theory. This is not going in your foldable because it's the theory, but then the law will. So plug in that was starting to write on yesterday. I think the last thing you drew was pictures of eggs and bottles, probably. Okay. All right. So remind yourself what a theory is. Talk in your group for about 30 seconds. What is a theory? All right, come back to me. 3, 2, 1. Mavericks table. Give me what you guys think on what a theory is.
It is a non-proven idea.
Okay, so I'm going to suggest that it's heavily supported with data and experiments, though. So literally in science, we cannot prove anything because there's always an anomaly or some data that could just throw it off and say, well, this didn't happen this time. So we have well-supported ideas, right? It is an idea that's super well supported with lots and lots of experiments. However, it's all just theoretical until we see it in action. So what we like to call this theory is the KMT. So write down KMT, kinetic molecular theory. And it is talking about how gases behave, or how we think they should behave, based on all this data we've suggested, or we've seen. So what we hope is that our theory of gases, the kinetic molecular theory of gases, we're hoping it describes how gases behave in an ideal fashion. Raise your hand if you think you're my ideal student. Some of you guys are super proud. You're my ideal student. So what do you think my ideal student is? What do you think they do? Essie is getting something you think
Has a name, Ryan Mister.
Oh, really? It's not on the list. Something else? Come on, does their homework, comes to class on time, happy, excited to be here, wears their safety glasses and their shoes every time we're in the lab, answers questions out loud, not just thinks the answer, is engaged in class. I mean, most of you guys are really close to my ideal student. All right, so now, think of your ideal man or woman. Think about it. I don't want to know, okay? Think about it. So mine, he helps me walk the dogs. He makes coffee for me every morning. He goes grocery shopping just willingly. Let's see, does the laundry. I mostly am describing my husband. He does all this. Goes running with me. Huh? Oh yeah, if I'm working, he's going to go. And even my clothes. Mine just is. Run like half marathons with me. It's the only thing he's not done yet. So let me just tell you, your ideal person, whatever you're thinking of, does not exist. There's something that you're going to have to compromise on in life. Maybe they have body odor. Maybe they sleep and snore. Maybe they're not timely. There's something you're going to compromise, but you'll probably get 90% of what you're looking for. I'm not like totally killing your dreams, right? Okay, so what we like to assume is ideal gases, like your ideal person, you're hoping they exist out there, but you're going to have to compromise a little bit. They don't. Okay, so the kinetic molecular theory, we're describing ideal gases, but they legitimately don't exist. But if we assume they exist, our life is so much easier. The math is easier, we can sleep at night, everything is easier if we assume the ideal person or gas exists out in the world. So these are the characteristics that we assume gases have. We assume, because we want our life to be easier so we can sleep at night, okay? So ideal gases have no volume. I mean, come on guys, they're matter, right? Does matter have volume? Yes or no? Yes, but if we make the assumption they don't have any volume, we don't have to account for that volume. We don't have to account for the space they take up from their container. So if I'm like, hey guys, we're dealing with the 1 liter container, we assume we have a full 1 liter to play in. But if I assume that they have volume, we're like, crap, now we gotta subtract the gas volume, figure out how much volume the container is now. It's just too much. Do you see why we make this assumption? To make our life easy, okay? So we're saying ideal gases have no volume, meaning they don't take up any significant amount of space. But for real gases what? Have volume, okay? So they do have a significant amount of space that they take up. But if we assume they don't, our math is easy peasy, okay? Another assumption we make is that they are in constant, or ideal gas particles are in constant random motion. Constant random motion. Is there anything that would influence a gas particle to not be randomly moving? Think about it. Constant random motion. What would cause particles to attract to each other? I heard someone say it. IMFs, right? We know, honestly, IMFs exist. So real gases, IMFs, attract them. And if they're attracting, they're not moving randomly. If they're not moving randomly, they're not colliding with the container walls. And if they're not colliding with container walls, our pressure is totally screwed up than what we thought it would be. So we make the assumption they are randomly moving, so we don't have to deal with any pressure adjustments, making our life easier. Okay, this one kind of relates. Whenever we're talking about particles moving, when they do collide, we're hoping they have an elastic collision. Do you guys know what that means? Elastic? You're thinking like a slinky, like elastic or like a rubber band. Basically, when they hit, they're not going to lose any kinetic energy. All the kinetic energy stays within, but we know for real what happens when things collide. Think of the little Newton's cradle thing. If the energy is transferred and maybe lost a little bit to friction or to heat, and then slowly rises up into the Newton's cradle thing. Eventually it will stop. Eventually, over like a couple of hours. But ideal gases, we assume they have elastic collisions, meaning no kinetic energy is lost. They're moving the same speed at all times. But for real, what's happening? Real gases what? Contrast this. What do you think? Right. In collisions, they lose some kinetic energy, which makes them slow down. If things slow down, are they going to hit the container wall as often? No, just because slow things are not moving to collide as often as they once were. Two more for you. This one's actually a true statement on all terms. You should be writing down the thoughts or these are the details of the kinetic molecular theory that you're required to know and make your assumptions on. All right, so for an ideal gas, kinetic energy is proportional to the Kelvin temperature. So haven't we seen this before? We saw yesterday the definition of temperature was what? Average kinetic energy, right? So I'm going to go ahead and show you guys the rest of that there. So temperature is equal to, or proportional to, kinetic energy average. This is true always for ideal gases and for real gases, because we are just basically making an assumption that hot things move fast, cold things move slow, and that generally is a good assumption. And this number 5, this 5th bullet point, who does this one correlate with that we already wrote down? Which number bullet up here? It correlates with the second one, right? Because we're basically saying if we assume they don't attract or repel, we're assuming they're constantly randomly moving. But we know that assumption is incorrect overall because IMFs. All right, so again, why are we making all of these just random assumptions? Make our life easier so we don't have to adjust for pressure differences or temperature differences or volume differences when we're dealing with real life gases. So we're still in introduction to chemistry, right? We're not trying to do calculus right now. We're doing algebra, which is why our math needs to remain simple. Give me a thumbs up when you're good with this kinetic molecular theory. Okay, so we're gonna talk about two more like thoughts behind the kinetic molecular theory, because there's some certain assumptions we continue to make because these are what we assume, and then we're gonna do a calculation. Okay, so this is a graph that's supposed to indicate a relationship between pressure, volume, temperature, and a constant. And so it's showing you like our ideality. This would be an ideal behavior, just 100% equal to whatever this variable system implies. But you'll notice that nitrogen, methane, hydrogen, and carbon dioxide all skew from the ideality upon differences in pressure. So we're looking and we're saying these are real gases, and this is an ideal situation. There's definitely some differentiation there, which we assume because we talked about all that already. But what you should understand is that real gases, or the characteristics of real gases, they're most prominent under certain conditions. So you really see the real behavior of a gas under these conditions: high pressure and low temperature. So those are the two conditions you should relate to the most exhibited characteristics of real gases. Why would, oh, you guys got your box of air? Box of air, okay. Okay, make it go under high pressure. What are you doing? Squish, 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 squish. Okay, so now you've basically put these particles from a box this big to a box this big. What are these particles basically going to have to do when they're that close to each other? Well, we've compressed them, right? But what are they going to do in here in the box together? Like, hey, girl, let's go to the mall. Let's interact. Let's do some I-mething. Let's have some attractions. Let's repel. Like, there's all kinds of things happening now. When they were this far apart, they didn't even know they had a neighbor. They were so far apart. So here, IMFs come into play like crazy. Okay, so now are they acting ideally? Yeah, your name? Not at all, right? Okay, get up. All right, you are a gas particle. You're a gas particle. You're under high temperature. Act like a high temperature gas particle. Please don't hit anything. Don't hit anything or anybody. Not hard anyway. Alright, and I'm cranking the temperature real low. Alright, and then you guys should start to do what? I mean, you're slowing down, but you're also condensing a little bit, and you're like, and you're okay. Now you've got to be near somebody, so you're condensing. Look at these attractions and IMFs. Is this ideal behavior? Is it? Yeah. Nay. Okay, let's sit down. You don't have to touch anybody else. Okay. Okay, so two conditions for non-ideality: high pressure and low temperature. Moving slow makes you interact. Close together makes you interact. Are we good with that? Yeah. Okay, a lot of common sense here works out. These are properties that we already kind of know about gases, but what now we're saying is that the kinetic molecular theory supports our thoughts, because we make these assumptions all the time. We were like, yeah, we know gases have low density because there's a lot of space they take up, but how close together are they? They're just not close together. They're under a high volume, but they're really spread out. So is there a lot of mass in this picture? A lot of mass with your name. Look, there's like 10 particles. No, there's not a lot of mass. So the mass is low or the volume is high, so the density is decreased because of that relationship. So we already knew gases have low density because they float, like balloons float. We know they can be compressed because what's between this particle and this particle? Empty space, nothing, right? So we can compress them by squishing them together. They're compressible. If you're not writing anything else down, at least write the bolded words down, because those are properties that we understand about gases, and I expect that you would remember those. We know that the gases can diffuse. Diffuse, who's ever heard of diffuse or diffusion? Who has a diffuser at home? Okay, we're the cool people here. Okay, so diffusion basically, if I brought in a box of Krispy Kreme donuts, who's actually ever had Krispy Kreme donuts on something? You live in. All right, so if I brought in a box of Krispy Kreme donuts and that was heated up, who would be the first people to smell them? These guys right here, right? Because it's what are the particles in the box? They're under what kind of concentration? High concentration, and all your noses are the low concentration, and then they would diffuse, and then maybe a minute later, Chandler and Kendall would start to smell them. So, in Salisbury, I'm not driving Salisbury. Okay. So diffusion from high concentration to low concentration. Brackets, these brackets mean concentration, by the way. It's another abbreviation. And then who's ever heard of effusion or effusion? It's not one that you've probably heard of, probably, but now if you realize it's very similar to diffusion, but it's in a specific scenario. Who's ever popped a balloon? By accident, of course. We don't pop balloons. It's just unkind. So the hole that you create in the balloon is the scenario where effusion would then occur. So it's basically diffusion through a hole. And so the gas particles move from high concentration to low concentration over time. And that balloon would deflate. All right, give me a thumbs up when you have your property. All right, now open up your foldable to the ideal gas page, ideal gas law page. It's what, like the 5th one-ish back? If you have all your titles on there, you should be fine. If not, Title 1 now, ideal gas law. And write this information down, and we're going to do a calculation with it. You maybe already have some information on there, but you can definitely include a little bit more. Everybody should have a foldable out. I'm basically trying to do this with you in class, you have to do it on camera. So the ideal gas law is supported by the kinetic molecular theory, and they kind of takes into all the assumptions that we've made, so we can calculate individual characteristics or individual properties or variables about a given scenario. Everything we've done before, though, has been 2 scenarios, P1 and P2, or T1 and T2, or V1 and V2. Those have been 2 scenario bases. So like, you start at the top of the mountain and you go to the bottom of the mountain. How does your balloon size change? Or you were driving in Florida and then you drove to New York. How does your tire pressure change under those different temperatures? This is not a two scenario system. We have 1 pressure, 1 temperature, 1 volume, and 1 amount. R is our new thing. It's called the constant, or the universal gas law constant. And this is a number you will write 1,000,000 times. We're all going to get tattooed. Just this, because we have to memorize this sucker. Okay? So 0.0821. Atmospheres times liters is on the numerator, because it's a big chunk of a unit, divided by moles times K. K stands for Kelvin. Okay, so note that is a numerator and a denominator, so it's going to help us cancel out all the units that are included. So if we have to use these, what does pressure have to be recorded in? Atmospheres, good. What does volume have to be recorded in? Liters. What does amount have to be recorded in? Moles. And temperature? Kelvin. So those units must be included in this law here, so all the units will cancel and we'll successfully calculate. Thumbs up when I'm good. All right, so follow that constant. It will help you. Well, we just did 1 through 16. You have 17 next. That's on the same paper. Mine's teeny tiny up here, but I'm going to use mine to prompt you where you should go. Okay, so 17, here we go. I would just do this on the same paper you were doing 1 through 16 on. You're going to keep going. We're going to do 17, 18, and 19 here together. We have plenty of time. We're doing great. All right, so I'm going to just read the question, and you guys can tell me what information is important. A student collects 425 milliliters of oxygen gas at a temperature of 24 degrees Celsius and a pressure of 0.889 atmospheres. How many moles of oxygen does the student collect? How many grams of oxygen is this? All right, Bailey's table, give me something that's important. Say that louder for me. What variable is that expressing? So V for volume, 425 milliliters. Back table over here, Kendall's table, another. Okay, and you already know what we have to do with that. Say again? What is that in Kelvin? 297, right? Kelvin, okay. Something else up here, Wesley's table? So we're just going to say P because there's no indication of any other pressure. So 0.889 atmospheres. All right, is there anything else, guys? I know there's not another given per se, but what else is asked of? Okay, so we're looking for what variable? N, so amount in moles. It also asks us moles and then grams, which we can totes do. That's just stoichiometry. And then there's going to be, we look at V, T, P, and N. We're missing something still. R, right? What's the R value?
Universal.
Give me 0.0. That's not it. Keep going. Atmospheres times liters over moles times K. Okay, I want you to write that down for these three at least because you'll get the hang of how to write it. So we now can look at R and see what values agree. Does pressure agree? Units wise. Check, that's atmospheres. Does liter agree? No. Can you guys do that in your head? What's that in terms of liters? Okay, so we're going to take that and divide it by 1,000, which is backing it up 1, 2, 3 places. So that's 0.425 liters. Does mole agree? Yes, that's what we're looking for. Do it. Kelvins agree. Yeah, we already converted. Thank you. Okay, so all this is going to get plugged into what law? Okay, so that's PV equals nRT. Notice this is the same flow we went through yesterday. 1, write your variables. 2, determine the law. 3, isolate the variable that's asked of you. So I think that's your best route. So which variable are we looking for? N, so how do I get N by itself? Good, divided by RT on both sides to cancel out RT over here. So therefore N is just equal to the numerator PV over denominator R times T. So that's all we're plugging in. So here we are, we're plugging in what here? What's the pressure? 0.889 atmospheres times the V of 0.425 liters. I'm squeezing it here. Divided by the big honking constant, 0.0821 atmospheres times liters per mole times K. And temperature of 297 Kelvin. Alright, so I squeezed my own here. You guys good? What units should cancel from the numerator? Liters on top and liters on the top of the bottom. So we're good here. What else? ATM on top, ATM on the bottom. What else? This would be hard to see, but do you see Kelvin here twice? This one is in the numerator of the denominator, and this one's in the denominator of the denominator. You picking up what I'm putting down? Yes. There's still like a fraction here. There's still a top and bottom in terms of the units in the denominator. So the top of the denominator and the bottom of the denominator can cancel. What's the only unit remaining? Moles, hallelujah, right? Because that's what we're looking for. And that's going to be copy dotted flopped to the top. All right, calculate. Make sure you put that in your calculator correctly. Make sure your calculator knows who's a numerator, who's a denominator, because you know it's not that smart. Everybody has a calculator. Everybody should be calculating. Here? What are you looking here? 0.425 liters. Guys, and scooch over here. There's 2 empty seats right here. Here's an awkward place. Alright, confirm with your neighbor. And you can begin the second. Oh, no, lies. We've only done half the answer. We gotta get the grams, too. Alright, what's our moles? Point what? 0.1, oh, 01. How many sig figs do I need? Are there only 2? Oh, there were 3. Yeah, there's 3. So 0.015 what? That's only 2 sig figs. 5. So because it says 495, right? So that's 5, and that's moles of what gas? Look in the question. When it says oxygen gas, what does it want you to write? Good. O2. This is not singular oxygen. This is diatomic oxygen because that's what exists in its natural form in a stable way. So there's answer 1, and then how would we get to answer 2? What's the molar mass of O2? Good. So we have this many moles of O2. 1 mole of O2 weighs 32 grams. Point what? So we want 3 sig figs again, guys. 496 grams of oxygen. Good. All right, you're good to move on to number 2. I mean, sorry, 18. I think 18. You can move on to 19. That's totally fine. I do want to give you a tip on that one after you get through with setting up what you're able to.
I don't know, it might be, but the answer on the answer
What about 60?
We're good, we got it.
Okay. Oh, or just put a dot. Sorry. That's probably what I didn't have on there. Typing up these statistics is sometimes the bane of my existence. We don't have any amounts. We divide them Now we do. Now you understand what we have to do. Especially when you're cartoons. On 19, I think you can figure out what to solve for, but then maybe you don't have to do after that. But I know you can figure out what to solve for. It's just one missing variable. It's just because the mole of that. I know that's the same question. I wouldn't solve that. Right. Because I don't know, but how do I convert? So solve for moles and convert. Thank you. Not convert to grams, but solve baby steps. Solve for what? Okay, stop.
Like 0.918.
Yeah.
Oh yeah, you're right. Yeah. 0.918. It's 6.116. Yeah, I did it wrong.
Yeah.
Yeah.
So you gotta write it down all three of these. Ah. That's right. Bryce, move on to number 19, okay? Alright, give me a thumbs up if you're on 19. Alright, everybody's on 19, that's fine. So the question, I know the end question is to solve for what? The end question is to solve for what? Molar mass, right? We know the units for molar mass. What are the units of molar mass? Molar mass is equal to grams per mole. So in the end, final step, you are going to solve for molar mass by literally dividing grams by moles. Which of these variables do we already have in the information?
Grams.
We already have this, right? So what's our true question? Solve for what? Moles, which is in the PVs and RT. And then you can go from there, okay? Go.
Yeah. So we don't put what do you have for the mole now? 0.00395. It's 0.918 atmospheres. 0.1. Yeah, that's what it is. That's the right answer.
So you do times divided by 0.918
Liters.
Yeah.
It's right there.
Times this year you know.
283. That's all I have.
Yeah, I have
Yeah, so I did 0.918, 0.1, divide that by 0.821, divide that by 280.
now I got
So it's just huge.
so is it 0.00?
I'm not recording that to correct sig figs because it's not really an answer. I'm not going to round because it'll cause rounding error later on. So that's why I did not record that to a particular decimal point.
I think I have.
You just divide it by 5. Do we do 20?
You're good. Let's almost 10 o'clock.
So,
63, yeah.
do we just go back and do it?
We're going to, I'm letting everybody finish real fast so we can look at finishing it some more detail.
Yeah, I can do
We are finishing it for next week, but you can do everything we've done so far. Okay?
If you get done and add some more detail to your phone call, you know what's required there. I can always go back to the first page, and I'm leaving this here for everyone. Get some color on there, it's just pencil, jazz it up a little bit. Jazz it up, you're fine, you've got a couple minutes to finish 19. Get some color on there. Get some real life examples, draw some pictures.